What if I told you the fabric of space itself is constantly rippling all around us like waves on an invisible cosmic ocean? These aren't ordinary waves, though. They're gravitational waves, distortions in the very geometry of the universe, first predicted by Albert Einstein over a century ago. But here's the wild part. It took us nearly 100 years just to catch the faintest whisper of them. Imagine something so powerful it bends space-time itself, yet so subtle, we needed the most precise machines ever built just to prove they exist. That's the paradox of gravitational waves, both earth-shattering and elusive, rewriting the laws of physics while hiding in plain sight. Now picture this: every time two black holes collide or neutron stars spiral into each other, they send these ripples racing across the cosmos at the speed of light. These aren't just cosmic fireworks, they're messages carrying secrets about the birth of galaxies, the nature of gravity, and even the origins of the universe itself. And the craziest part, we're only just beginning to decode them. Over the past few decades, scientists have peeled back layer after layer of this cosmic mystery, uncovering 30 groundbreaking discoveries that have turned astrophysics upside down. From catching the echoes of black holes merging billions of years ago to spotting the fingerprints of the Big Bang, gravitational waves have become our backstage pass to the universe's most spectacular events. This isn't just science, it's a detective story on the grandest scale. Think about it, we're using ripples in space-time to spy on collisions that happened before Earth even existed. Every new detection is like finding a piece of a puzzle we didn't even know was missing. And what we've learned so far, well, it's blown the doors wide open on questions we thought were unanswerable. How do supermassive black holes grow so big? What happens when matter gets crushed into the densest objects in existence? Could there be entirely new dimensions hidden in these waves? Strap in, because today we're diving into 30 of the most jaw-dropping discoveries gravitational waves have revealed. And trust me, by the end, you'll never look at the night sky the same way again. The moment that changed everything came on September 14, 2015. Deep underground in two identical facilities over 3,000 kilometers apart, one in Louisiana, the other in Washington state, LIGO laser beams flickered. Not by much, the disturbance was smaller than the width of a single proton, but that microscopic wobble carried an earth-shaking message. Gravitational waves had finally been caught in the act. What LIGO had intercepted were the death throes of two black holes, each about 30 times the mass of our Sun, locked in a fatal dance over 1.3 billion years ago. As they spiraled inward at half the speed of light, their collision unleashed a tsunami in space-time, warping the fabric of the universe so powerfully that when the ripple finally reached Earth, it stretched and squeezed our entire planet by a fraction of an atomic nucleus. This wasn't just a scientific triumph, it was a validation of Einstein's wildest dream. A century earlier, his equations had predicted these ripples should exist, but even he doubted we'd ever detect something so faint. LIGO proved him wrong with the most sensitive rulers ever built. Twin laser interferometers so precise they can measure distances 10,000 times smaller than a proton. Picture this, each facility fires a laser beam down 2-4-kilometer long vacuum tubes where mirrors bounce the light back and forth hundreds of times. If a gravitational wave passes through, it literally changes the length of one tube relative to the other by less than 1/10,000th the width of a proton, and LIGO sensors caught that difference. The discovery sent shockwaves through the scientific community. Within months, the finding was confirmed, and by 2017, three pioneers behind LIGO, Rainer Weiss, Barry Barish, and Kip Thorne, were awarded the Nobel Prize in Physics. But the real prize was what this meant for astronomy. For the first time, humanity had gained a whole new sense, like opening ears after only ever seeing the universe. Before LIGO, black hole collisions were theoretical. Now we could hear them. The event even had a name, GW150914, marking the exact date of detection like a cosmic birth certificate. And this was just the beginning. That first chirp, lasting less than a fifth of a second, unlocked a new era where space-time itself carries messages from the darkest, most violent corners of existence. That first detection was just the tip of the cosmic iceberg. In the years following GW150914, LIGO and its European counterpart Virgo began picking up gravitational wave signals like a cosmic drumbeat, sometimes monthly, sometimes even weekly. Each new chirp told the same shocking story. Black holes weren't just merging occasionally. They were crashing into each other all across the universe, far more often than anyone had dared to predict. One detection might have been a fluke, but dozens that changed everything we thought we knew about how black holes live and die. Take the event catalog from just the first 3 observing runs. Scientists logged over 50 confirmed black hole mergers, revealing pairs with masses ranging from a few times that of our Sun all the way up to monstrous 80 solar mass behemoths. Before LIGO, theorists had guessed maybe a few mergers per cubic gigaparsec of space per year. The real number turned out to be closer to 20, meaning somewhere in the universe 2 black holes collide every 10 minutes. Wrap your head around that scale for a second. While you've been watching this video, at least one pair of these cosmic titans has already smashed together in some distant galaxy, sending ripples through space-time we might detect years from now. What makes this even wilder is how it's forced us to rethink black hole formation. Many of these merging pairs are way too heavy to have come from regular collapsing stars. Some spin in directions that suggest they weren't born together, but got flung into each other's orbits later, like celestial bumper cars in crowded star clusters. Others show hints of hierarchical mergers, where 2 black holes collide to form a bigger one, which then merges with yet another. It's a black hole eat black hole universe out there, building up these gravitational wave behemoths generation after generation. And the implications, they're rewriting astronomy textbooks. If mergers are this common, then supermassive black holes, the kind lurking at the center of galaxies, might grow not just by swallowing gas, but by devouring smaller black holes in an endless cosmic feast. It suggests the universe is far more violent and dynamic than we imagined, with black holes constantly reshaping their neighborhoods through these catastrophic collisions. Every new detection adds another piece to the puzzle, revealing a universe where space-time isn't just the stage for these events, it's the messenger, carrying their stories across billions of light years directly to our detectors. Then came the cosmic event that rewrote the rules, GW170817. On August 17, 2017, gravitational wave detectors picked up a signal unlike anything seen before. Instead of black holes producing a quick chirp, this was a drawn-out crescendo lasting nearly 100 seconds. Within seconds of the detection, telescopes around the world received an alert. 2 neutron stars, the super-dense corpses of dead stars, had just collided 130 million light-years away in a galaxy called NGC 4993. This wasn't just another ripple in space-time, it was a full cosmic fireworks show. For the first time in history, astronomers didn't just hear the event through gravitational waves, they saw it. Gamma-ray telescopes caught a burst of high-energy radiation just 2 seconds after LIGO alert. Then optical telescopes spotted a glowing kilonova, an explosion 1,000 times brighter than a typical nova flaring up like a beacon in the night. This was multi-messenger astronomy at its finest. Gravitational waves, light, and radiation all telling the same story from across the universe, but the real shocker was what that glow revealed. As the neutron stars spiraled into each other, their collision spewed out a cloud of material packed with free neutrons. In this extreme environment, atoms got ripped apart and reassembled in ways impossible under normal cosmic conditions. And that's how we got answers to a question that had puzzled scientists for decades. Where do heavy elements like gold, platinum, and uranium come from? Turns out your wedding ring was forged in a neutron star collision. The spectra from that kilonova showed unmistakable signatures of freshly created precious metals. Estimates suggest the event produced roughly 10 times Earth's mass in gold alone. Picture that an entire asteroid's worth of gold synthesized in seconds, then scattered across the cosmos. It confirmed what theorists had long suspected. Neutron star mergers are cosmic alchemy labs, responsible for creating half the periodic table's heaviest elements. Beyond bling, GW 170817 solved another mystery. For years, astronomers had debated whether short gamma-ray bursts, those incredibly energetic flashes lasting less than 2 seconds, came from neutron star collisions. This event nailed it. The gravitational waves arrived first, tracing the star's death spiral, followed by that 2-second gamma-ray burst. It was like catching a criminal on video, with multiple witnesses all corroborating the same story. The aftermath was just as groundbreaking. Over weeks, the kilonova's glow shifted colors, revealing layers of ejected material like peeling an onion. Radio telescopes later detected a jet of particles moving at 99.9% the speed of light. Proof these collisions can launch some of the universe's most extreme particle accelerators. Every wavelength, from X-rays to radio waves, painted a richer picture than gravitational waves alone ever could. That's why this detection marked a turning point. Before, gravitational wave astronomy was like hearing a symphony with your eyes closed. Now we could finally see the orchestra. It proved that combining gravitational waves with traditional astronomy isn't just useful, it's revolutionary. Suddenly, we had a new way to measure cosmic distances, test general relativity in extreme conditions, and even probe the elusive equation of state of neutron stars. How these ultra-dense objects behave under pressures that crush atoms into exotic forms of matter. What's wild is how much luck was involved. The collision happened relatively close by cosmic standards, and just 2 weeks earlier, LIGO had upgraded its sensitivity. Had it occurred a month later, the detectors would have been offline for maintenance. Instead, humanity got front-row seats to one of the universe's rarest and most spectacular events. A golden collision that didn't just confirm theories, but minted them into scientific fact. That chirp, that brief, almost musical blip became the sound of scientific history. When LIGO scientists first played the audio version of GW 150914 at their press conference, it wasn't just a technical reveal, it was a moment of human connection to the cosmos. Here's how it works. Gravitational waves don't make sound in space, of course, but by shifting the frequency of the signal into the range of human hearing, researchers created an auditory fingerprint of 2 black holes merging. The pitch rises sharply as the objects spiral faster, climaxing in that distinctive chirp at the moment of collision, like a cosmic bird call announcing the birth of a new black hole. The sound's simplicity hides its profound meaning. Each millisecond of that chirp encodes physics Einstein only dreamed of testing, the initial low frequencies. That's the black holes orbiting each other dozens of times per second. The rising tone, their death spiral accelerating to hundreds of orbits per second as they lose energy to gravitational waves. And the abrupt cutoff, the instant they merge into a single, wobbling black hole ringing down like a struck bell. Scientists can extract the masses of the objects, their distances, even their spins, just from those fractions of a second of audio. But why did this particular sound capture the world's imagination? Partly because it made the abstract tangible. You could close your eyes and hear space-time bending. The chirp went viral, sampled in electronic music, used as smartphone ringtones, even featured in a Grammy-winning album. It became a cultural shorthand for discovery itself, proof that the universe speaks in rhythms we're only beginning to understand. Artists and scientists collaborated to turn raw data into stunning visualizations. spiraling waveforms, ripple simulations, even 3D printed sculptures of the sound's mathematical structure. The chirp also shattered misconceptions. Before LIGO, many imagined gravitational waves as literal sounds in space, but the truth is far more poetic. These waves are space-time itself stretching and squeezing, a silent symphony transcribed into sound for our ears. That translation process is its own marvel. LIGO raw data looks like chaotic noise until supercomputers filter out earthquakes, passing trucks, even ocean waves. What remains is a signal 10,000 times smaller than the background static, a whisper extracted from a hurricane. What's wild is how much personality these chirps have. Compare GW150914's sharp whoop to the deeper, slower chirp of a massive black hole merger, or the drawn-out crescendo of colliding neutron stars. Each tells a distinct cosmic story. There's even humor in the names scientists give them, like the GW190521 detection nicknamed the Scratch because its signal resembled a record needle skipping. This auditory approach isn't just for public outreach. Researchers literally listen to the data, training their ears to spot anomalies like musicians tuning instruments. Some have even identified potential signals by ear before algorithms flagged them. It's a reminder that science, at its heart, is a human endeavor, one where intuition and technology dance as intimately as those distant black holes. And every new chirp adds another verse to the universe's ongoing song. Einstein's theory of general relativity has survived every test thrown at it for over a century, but gravitational waves opened a door to the ultimate proving ground. Near black holes, where gravity twists space-time into knots, the rules of physics reach their breaking point. This is the strong field regime, a place so extreme that even light can't escape and intuition fails. Until recently, testing Einstein here was like trying to study a hurricane by watching from space. Gravitational waves changed everything. They let us step inside the storm. Take the infamous ring-down phase after two black holes collide. As the newborn black hole settles, it vibrates like a struck bell, emitting gravitational waves at specific frequencies. General relativity predicts these tones should fade in a particular way, a cosmic fingerprint. When LIGO analyzed GW150914's ringdown, the data matched Einstein's equations to within 99.9% accuracy. Think about that. A theory conceived on paper in 1915 perfectly described the behavior of warped spacetime around a 30 solar mass black hole over 1 billion light-years away. But the real surprises came when scientists looked for tiny deviations, hints of new physics. Some mergers show hints of echoes in their ring-down signals, faint repetitions that could suggest black holes aren't the perfect, smooth objects relativity predicts. One theory, these echoes might betray quantum effects at the event horizon where gravity's rules could blur. Others propose they're statistical flukes, but the hunt is on. Then there's the speed test. According to relativity, gravitational waves must travel at light speed. When GW170817's neutron star collision arrived with its gamma-ray burst just 2 seconds later, it confirmed this to within 1 part in a quadrillion. Perhaps the most mind-bending test involves black hole hair, or rather, the lack of it. General relativity says black holes are ball defined only by mass, spin, and charge, with no other distinguishing features. Gravitational wave signals so far support this. No matter how messy the collision, the final black hole always combs itself into this simple state. But some alternative gravity theories predict subtle departures, extra hair, in the form of gravitational wave memory or polarization patterns. Future detectors like LISA could spot these whispers of new physics. What's wild is how these tests push technology to its limits. To measure deviations from relativity, scientists need waveforms so precise they account for millions of possible collision scenarios. Supercomputers run for weeks simulating these cosmic crashes, creating templates to compare against real data. It's like having a dictionary of every possible way space-time can ring, then listening for typos. So far, Einstein's theory keeps passing, but the universe always has surprises up its sleeve. Every new detection sharpens our view, probing gravity in realms where a single cubic centimeter of neutron star material outweighs Mount Everest. And that's the beauty of this experiment. With each merger, we're not just confirming relativity, we're stress testing it at energies and densities unreachable in any lab. Somewhere in the data, there might lurk a crack in the foundation, a hint of quantum gravity or extra dimensions. Or perhaps Einstein's vision will hold, proving once again that genius sees further than we dare dream. Either way, gravitational waves have given us front-row seats to the greatest show in physics, the moment we find out if the universe plays by the rules we've written, or if it's been whispering new ones all along. Black holes might be the universe's ultimate minimalists. Despite their terrifying reputation, these cosmic predators carry surprisingly little baggage, just 3 defining traits: mass, spin, and charge. That's it, no frills, no extra features, no distinguishing marks. This idea, known as the no-hair theorem, has been a cornerstone of black hole physics for decades, but until gravitational waves came along, it was just an elegant mathematical prediction. Now, with each collision we detect, we're getting front-row evidence that black holes really are as simple and as strange as Einstein's equations suggest. Think of it like this: toss any object into a black hole, a star, a spaceship, an entire library's worth of books, and all that information gets crushed down into just 3 numbers. It doesn't matter if what fell in was made of gold or granite, whether it was spinning clockwise or counterclockwise. The black hole swallows it all and emerges with only its mass slightly increased, its spin subtly altered, and its charge, if it had any, barely changed. This radical simplicity defies intuition. How can objects so complex vanish without a trace, leaving behind no fingerprints of their past? Gravitational waves are the perfect tool to test this cosmic amnesia. When 2 black holes spiral toward collision, the shape of their gravitational wave signal encodes everything about them: their masses, how fast they're spinning, even how they're oriented in space. But after the merger, when the newborn black hole starts ringing down, those waves carry only its final mass and spin. No echoes of its violent birth, no scars from the objects it consumed. It's as if the universe hits a reset button, erasing all traces of the chaos that came before. This isn't just philosophical, it's measurable. Scientists compare the gravitational waves emitted during a black hole collision's in-spiral phase, where you can still see the individual objects, with the ring down where only the final black hole remains. The data so far shows an eerie match: no hidden features, no extra hair, just clean, simple waveforms that align perfectly with the no-hair theorem's predictions. Even when black holes merge in messy, off-center collisions, the resulting object always smooths itself out, shedding any irregularities in a storm of gravitational radiation. But here's where things get interesting. Some alternative theories of gravity suggest black holes might secretly harbor hair at tiny deviations from Einstein's predictions that could hint at new physics. Maybe quantum effects near the event horizon leave subtle imprints, or extra dimensions twist space-time in ways we haven't imagined. Gravitational wave detectors are now sensitive enough to hunt for these whispers. So far, nothing conclusive has turned up, but the search is on. Every new black hole merger is another chance to catch the universe breaking its own rules, or to marvel at how stubbornly it sticks to them. What's truly mind-bending is how this simplicity hides unimaginable complexity. A black hole's event horizon might look featureless from the outside, but just beyond that point of no return, space-time is churned into a frenzy. The no-hair theorem doesn't mean black holes are boring. It means all their wildness gets locked away, hidden behind a veil of mathematical elegance. Gravitational waves give us a backstage pass to this cosmic magic show, letting us watch as the universe tidies up its most chaotic acts into three neat numbers. And with each collision we detect, we're not just testing a theory, we're learning how spacetime itself handles its darkest secrets. For decades, black holes seem to come in just two sizes, stellar and supermassive, like cosmic missing links in an evolutionary chain. But gravitational waves have exposed a hidden middle child, intermediate mass black holes, tipping the scales at hundreds or even thousands of solar masses. These elusive giants bridge the gap between star-sized black holes and the monsters lurking in galactic centers, solving one mystery while spawning even bigger questions about how the universe builds its most extreme objects. Take the event GW190521. When LIGO and Virgo detected this merger in May 2019, the data revealed something unprecedented. One of the colliding black holes weighed in at a staggering 85 solar masses, far too heavy to form from a collapsing star, yet nowhere near supermassive territory. The kicker, its partner was a more typical 66 solar masses, creating a final black hole over 140 times the mass of our Sun. This wasn't just another stellar remnant, it was the smoking gun for a whole new class of black holes astrophysicists had hunted for years. The existence of these mid-sized behemoths cracks open a cosmic chicken and egg problem. Supermassive black holes weighing millions or billions of solar masses anchor nearly every galaxy we see, but how do they grow so large so fast? Intermediate mass black holes could be the seeds formed in the early universe from collapsing gas clouds or runaway mergers in dense star clusters. Imagine them as cosmic stepping stones, gluing together smaller black holes over eons until they reach supermassive status. But why are they so rare? Part of the answer lies in their Goldilocks nature. Forming an intermediate mass black hole requires just the right conditions, a dense environment where smaller black holes can collide and merge repeatedly, but not so crowded that gravitational interactions fling them away before they can grow. Ancient globular clusters, tightly packed balls of stars orbiting galaxies, might be perfect black hole nurseries. Some even show telltale X-ray glows hinting at hidden middleweights at their cores. Yet even this doesn't fully explain their scarcity. Another clue comes from their distinctive gravitational wave signatures. While stellar mass mergers produce quick, high-pitched chirps, intermediate mass collisions emit deeper, longer rumbles, like comparing a violin's pluck to a cello's sustained note. LIGO detectors have to be exquisitely tuned to catch these lower frequency waves, which might explain why we've spotted so few. What's truly fascinating is how these discoveries rewrite black hole formation rules. That 85 solar mass object in GW190521, it defies conventional physics. Stars between about 60 and 130 solar masses don't collapse into black holes. They undergo explosive pair instability supernova that obliterate them completely. So how did this one survive? One possibility: it's a second-generation black hole, itself the product of earlier mergers in a cosmic game of LIGO where smaller black holes snap together to build something unprecedented. Every new intermediate mass detection peels back another layer. Some show spins suggesting violent past collisions, while others move at peculiar velocities, hints they might have been kicked out of star clusters during chaotic mergers. Each clue points to a universe far more dynamic and interconnected than we imagined, where black holes don't just lurk silently but actively sculpt their environments through gravitational encounters. The hunt for these missing links is far from over. Upcoming detectors like LISA, a space-based gravitational wave observatory, will specialize in catching the low-frequency ripples from even larger mergers, potentially spotting intermediate mass black holes in the act of merging into supermassive giants. It's like tuning into a new radio station broadcasting the universe's most dramatic growth spurts. And with each detection, we're not just filling a gap in our classification charts, we're watching the universe solve its own black hole puzzle, one violent merger at a time. For nearly a century, astronomers have been locked in a cosmic detective story with high stakes pinpointing exactly how fast the universe is expanding. This number, called the Hubble constant, is more than just a speed limit. It's the key to understanding everything from the age of the cosmos to its ultimate fate. But here's the twist: two of science's most trusted methods for measuring it disagree. One approach, using distant supernova as cosmic mile markers, gives one value. Another, studying the faint afterglow of the Big Bang with space telescopes like Planck, gives another. The difference might seem small, just a few percentage points, but in cosmology, that gap is a chasm. Enter gravitational waves, offering a third, completely independent way to settle the score. When neutron stars collide, they don't just send out gravitational waves, they also unleash a brilliant flash of light called a kilonova. This cosmic 2-for-1 deal gives scientists something extraordinary, a way to measure distance two different ways at once. Gravitational waves reveal how energetic the merger was, like hearing how loud a firework explosion is to gauge how far away it is. The light from the kilonova, meanwhile, shows how much the universe has stretched since that light began its journey, its redshift. Combining these gives a direct measurement of the Hubble constant, no cosmic ladder required. The results mind-bending. Early measurements from events like GW 170817 landed smack in between the supernova and Planck values, deepening rather than resolving the tension. It's as if the universe is playing a prank on us, whispering contradictory clues through different cosmic messengers. Some theorists think this discrepancy might hint at unknown physics. Maybe dark energy isn't constant after all, or perhaps neutrinos have hidden properties. Others suggest unseen errors in our measurements lurk in the fine print. What makes gravitational waves so revolutionary here is their independence. Unlike other methods that rely on chains of assumptions, how bright supernova should be, or how matter should have clumped in the early universe, neutron-star mergers are self-calibrating. Their gravitational waves encode their intrinsic power, acting like standard sirens ringing across the cosmos. Every new detection tightens the measurement, with future observatories like the Einstein telescope poised to shrink uncertainties to razor-thin margins. This isn't just academic bean counting. The Hubble constant tension could be the first crack revealing a deeper layer of cosmic reality. If gravitational waves ultimately side with one camp over the other, it might force us to rewrite textbooks on dark energy or the early universe's evolution. Or worse, if they keep straddling the middle, we might need entirely new physics to explain why the universe can't seem to make up its mind. One thing's certain, every neutron-star collision isn't just a light show. It's a vote in the most consequential election in cosmology. Somewhere in the faint whispers of space-time, buried beneath the cacophony of black hole collisions and neutron-star mergers, might lie the ultimate cosmic relic: gravitational waves from the Big Bang itself. These primordial ripples, generated in the universe's first trillionth of a second, would be the oldest possible signal we could ever detect, carrying secrets from the very moment reality as we know it burst into existence. Think of them as the universe's first heartbeat, frozen in time and stretched across eons by the expansion of space. The hunt for these echoes hinges on a wild idea called cosmic inflation, the theory that the universe underwent an incomprehensibly rapid expansion in its first sliver of existence, growing from smaller than an atom to the size of a grapefruit in less than a blink. If inflation happened, it would have sent gravitational waves rippling through the fabric of space-time like shockwaves from a cosmic explosion. Today, those waves would be imprinted on the afterglow of the Big Bang, the cosmic microwave background, as a faint swirling pattern in the polarization of ancient light. Spotting that telltale swirl would be like finding fingerprints on the universe's birth certificate. So why haven't we caught them yet? The challenge is scale. These primordial waves would have wavelengths stretching across light years, far beyond what ground-based detectors like LIGO can sense. Instead, scientists are turning to the cosmos itself as a detector. Projects like the upcoming Light-Bird satellite and ground-based telescopes in Chile's Atacama Desert are scanning the cosmic microwave background with unprecedented precision, searching for that elusive polarization pattern nicknamed B-modes. It's like trying to read a message written in ripples on the surface of a pond after the pond has become an ocean. The stakes couldn't be higher. If found, these waves would confirm inflation and reveal energies 1 trillion times beyond what any particle collider could reach, a window into physics at the Planck scale, where gravity and quantum mechanics collide. Some theories even suggest primordial waves could carry hints of extra dimensions or the fabled quantum nature of gravity itself. But there's a catch. If we don't find them, it might mean inflation never happened, forcing us back to the drawing board on how the universe began. What's thrilling is how close we're getting. In 2014, the BICEP 2 team thought they'd spotted the signal, only to realize interstellar dust had fooled them. Today's experiments have learned from that lesson, cross-checking data across multiple wavelengths to filter out false positives. And the next generation of space missions, like the European Space Agency's proposed CMB-S4, could finally have the sensitivity to either catch the waves or rule out entire classes of inflation models. Imagine hearing the universe's first sound, a deep, resonant hum from before time had meaning. That's the promise of primordial gravitational waves. They wouldn't just rewrite cosmology, they'd connect us directly to the birth of everything, a message in spacetime's oldest language waiting to be decoded. And when or if we find them, it won't just be a discovery. It'll be the closest thing to time travel science has ever achieved. The cosmic stage is set for the ultimate gravitational wave showdown, one that won't play out in subterranean labs but in the silent expanse of space. While LIGO catches the high-pitched chirps of stellar mass collisions, an even more dramatic performance awaits detection. The slow-motion dance of supermassive black holes, each weighing millions or even billions of suns. These aren't the quick mergers we've grown accustomed to. Their epic, drawn-out affairs lasting years or even decades, emitting gravitational waves so low in frequency that they hum below Earth's detection range like the deepest notes of a cosmic double bass. Why the difference? It all comes down to scale. When two supermassive black holes spiral toward collision, they might orbit each other just once every few weeks compared to the frantic hundreds of times per second for their stellar mass counterparts. That leisurely pace produces gravitational waves with wavelengths stretching millions of kilometers, far too long for ground-based detectors to catch. Imagine trying to measure ocean tides with a centimeter ruler. That's essentially the challenge Earth-bound observatories face. That's where LISA comes in. The Laser Interferometer Space Antenna, slated for launch in the 2030s, will float 3 spacecraft in a perfect triangular formation 2.5 million kilometers apart, connected by laser beams. Free from Earth's seismic noise and with arms thousands of times longer than LIGO, this space-based detector will finally tune into the universe's low-frequency gravitational wave channel. Its prime targets, binary supermassive black holes pairs lurking at the hearts of merging galaxies, slowly tightening their orbits over cosmic timescales before their final cataclysmic collision. The science behind these binaries reads like a galactic thriller. When two galaxies merge, their central black holes eventually sink toward the new core through a process called dynamical friction. But here's the catch. Once they get within about 1 parsec, 3.26 light-years of each other, they stall. Theory suggests it could take billions of years for them to close that final gap unless something intervenes. That's where the detective work begins. Do dense star clusters or swirling gas disks provide the extra gravitational nudge needed? Or do some pairs remain stranded in what astronomers call the final parsec problem, forever circling just out of reach? LISA observations could crack this mystery wide open. By measuring the hum of these binaries across the universe, scientists will map out their populations, orbital distances, and merger rates. Some might be so close, just months or years from collision, that we could watch their orbits decay in real time. Others could reveal entirely new physics, like whether space itself drags around spinning black holes, an effect called frame dragging, or if their event horizons warp in unexpected ways. But the implications stretch far beyond black holes. These gravitational waves will serve as backlighting for the entire cosmic web. As they travel billions of light years, their paths subtly bend around intervening galaxies and dark matter clumps, creating a gravitational lensing effect that could map the universe's hidden structure. Some waves might even carry echoes from the chaotic early universe, when supermassive black holes somehow formed astonishingly fast after the Big Bang. The wait for these discoveries might feel agonizing, but it's worth remembering the signals we're chasing have been traveling for eons. Somewhere out there, two supermassive behemoths are already locked in their death spiral, warping spacetime with each ponderous orbit. Their song, a deep, resonant thrum older than Earth itself, is already rushing toward us at light speed. We just need to learn how to listen. Among the most extreme black holes ever discovered are those spinning at nearly the speed of light, cosmic whirlpools twisting spacetime itself into a frenzy. These rapid rotators defy intuition, packing the equivalent of hundreds of solar masses into a sphere smaller than Manhattan while revolving hundreds of times per second. How fast is that? Picture dragging the entire Pacific Ocean behind you as you sprint at 99.9% light speed. That's the kind of energy we're talking about. But these black holes aren't just cosmic oddities. Their breakneck spins are encrypted history books revealing how they gorged on matter, collided with peers, or even got kicked into overdrive by forces we're only beginning to understand. Take the black hole in GW 150914, LIGO first detection. Analysis showed one of the colliding objects was spinning at least 67% of the maximum possible rate Einstein's equations allow. That's not just fast, it's theoretical limit fast, but here's the puzzle. Not all black holes spin this rapidly. Some lumber along like cosmic tortoises, barely rotating at all. The difference comes down to their formation stories. A black hole born from the collapse of a single massive star might inherit only a modest spin, like a figure skater pulling their arms in slightly. But feed that black hole over millions of years through a whirling accretion disk, or slam it into another black hole at just the right angle, and it can rev up like a cosmic top, approaching those mind-bending speeds. The real surprise came when researchers noticed a pattern in the LIGO-Virgo merger catalog. Many of the most massive black holes, those above 40 solar masses, were spinning relatively slowly, while their mid-sized counterparts often clocked near the speed limit. This could hint at two distinct formation pathways. The heavyweights might grow mainly by gobbling gas from all directions, which doesn't efficiently transfer spin, like trying to speed up a merry-go-round by pushing randomly. Meanwhile, the middleweights could be products of earlier mergers, black hole offspring spun up by the angular momentum of their parents' death spiral. But the extremes steal the show. Consider GW 190521, where one black hole was spinning so close to the maximum it warped spacetime into a phenomenon called frame dragging, literally dragging the fabric of the universe around it like a spoon swirling honey. At these velocities, relativity gets weird. The black hole's event horizon flattens at the poles and bulges at the equator, while time for an object near the edge slows to a crawl. Matter orbiting just outside might reach velocities where centrifugal force alone could rip atoms apart, a cosmic shredder powered by spin. These observations are rewriting our understanding of black hole diets. Traditionally, astronomers thought black holes spun up steadily by feeding from orderly, rotating disks of gas. But the merger data suggests some might get speed boosts from messier meals like swallowing stars whole or merging with other black holes at off-kilter angles. It's the difference between sipping soup with a spoon and chugging it straight from the bowl. The implications stretch beyond black holes themselves. A rapidly spinning black hole can fire jets of plasma at near light speed, influencing entire galaxies. Its rotational energy might even be extractable through processes like the Penrose mechanism, a potential alien power source for civilizations millions of years ahead of us. And if we ever detect a black hole spinning faster than relativity's limit, that would be the first crack in Einstein's armor, a signpost toward new physics lurking in the extreme. For now, every new merger is a snapshot of these cosmic spin cycles, some black holes lazily twirling, others whirling like dervishes, each telling its own story of violence, gluttony, or celestial ballet. And with each detection, we're not just cataloging spins, we're piecing together the life cycles of the universe's most enigmatic objects, one dizzying revolution at a time. Gravity doesn't just bend light, it bends space-time itself, and that means even gravitational waves can get warped, twisted, and magnified on their journey across the cosmos. This bizarre phenomenon, called gravitational lensing, isn't just a cosmic curiosity. It's turning into one of our sharpest tools for mapping the universe's most elusive ingredient, dark matter. Normally, we detect lensing when massive objects like galaxies distort the light from background stars, creating eerie rings or multiple images of the same quasar. But when gravitational waves get lensed, the effects are far stranger and more revealing. Imagine a black hole merges gravitational waves traveling toward Earth for billions of years, only to skim past a supermassive galaxy cluster along the way. The cluster's immense gravity acts like a funhouse mirror, bending the wave's path and potentially splitting them into multiple copies of the same event. The result, we might detect the same collision more than once, with the lensed signals arriving days, weeks, or even years apart, like cosmic echoes staggered across time. The first hints of this emerged in 2020, when researchers noticed peculiar similarities between two gravitational wave events detected months apart. Could these have been duplicates of a single merger, lensed by an invisible mass? The evidence isn't conclusive yet, but the implications are staggering. Here's where dark matter enters the picture. Most lensing studies rely on visible matter to explain distortions, but there's never enough of it to account for the full effect. The mismatch points to dark matter's invisible scaffolding halos of mysterious particles weaving through galaxies. Gravitational wave lensing offers a brilliant workaround. Since dark matter warps spacetime just like normal matter, lensed waveforms would carry its fingerprint. By analyzing how these waves stretch, split, or delay, scientists could reconstruct the exact distribution of dark matter along their path, something traditional astronomy struggles with. The technique has another ace up its sleeve: precision. Light-based lensing gives blurry snapshots, but gravitational waves encode precise timing and phase information. A lensed waveform might show subtle interference patterns, like ripples crossing in a pond, betraying the mass and shape of whatever bent its path. Future detectors could even spot microlensing tiny deflections caused by star-sized dark matter clumps too small to lens light noticeably. It's like upgrading from a foggy window to an electron microscope for studying the universe's shadowy skeleton. And then there's the wild card: wave optics. Unlike light, gravitational waves have wavelengths so long, hundreds of kilometers, that they interact with lensing objects in quantum-like ways. Instead of clean multiple images, we might detect faint diffraction patterns, ghostly imprints of the lens's structure smeared across the signal. Decoding these could reveal whether dark matter is cold, warm, or made of primordial black holes, solving one of cosmology's longest-running debates. Every lensed gravitational wave is a cosmic Rosetta Stone, translating the invisible architecture of the universe into signals we can finally read. With enough detections, we'll assemble a 3D map of dark matter's distribution, uncovering filaments and voids that have shaped the cosmos since the Big Bang. It's a reminder that even spacetime's whispers don't travel straight. They curve, twist, and carry secrets in their bends. Black holes and neutron stars might dominate the gravitational wave spotlight, but lurking in the cosmic shadows are even stranger beasts, objects so exotic they blur the line between science and speculation. Picture a star made not of atoms, but of hypothetical particles so light they behave like waves across the cosmos, or a tunnel through space-time itself, connecting distant regions like a cosmic subway. These aren't just sci-fi concepts, they're potential gravitational wave sources called exotic compact objects, and their existence would rewrite the rules of astrophysics as we know them. Take boson stars, theoretical objects made of ultra-light particles like actions, which might constitute dark matter. Unlike black holes, these would have no event horizon or singularity. Instead, their entire mass could be a swirling, star-sized quantum wave. When two boson stars collide, their gravitational waves wouldn't end with a black hole's sharp ring down. Instead, simulations suggest their waveforms would oscillate strangely, like a bell struck with a mallet made of Jell-O, producing interference patterns no black hole could mimic. Some researchers even speculate that LIGO catalog might already contain hints of these events, certain detections with unusual after ringing that don't quite fit Einstein's predictions. Then there's the ultimate cosmic shortcut, wormholes. Often dismissed as mathematical curiosities, these space-time tunnels could leave gravitational wave fingerprints if they're ever destabilized or collide. Unlike black hole mergers, which produce a clean chirp, a wormhole merger might emit waves that echo bizarrely, as if space-time itself were folding and refolding like origami. The echoes would come from gravitational waves bouncing between the wormhole's throat and its exit, creating a signature no natural object could replicate. Some theorists argue that a handful of LIGO detections already show faint, repeating echoes, though the evidence remains hotly debated. The hunt gets even wilder with Gravastar's hypothetical objects where a black hole's singularity is replaced by a bubble of exotic vacuum energy. These would have surfaces so dense they'd reflect gravitational waves like mirrors, producing super-radiant scattering that could amplify certain frequencies. Imagine shouting into a canyon and hearing your voice return louder. That's the kind of effect Gravastar collisions might exhibit in gravitational wave data. The beauty of these searches lies in their no-lose proposition. Even null results help physicists constrain wild theories, ruling out entire classes of exotic objects. But if just one detection defies expectations, it could open a portal, sometimes literally, to new physics. Future detectors like the Einstein telescope or Cosmic Explorer, with their vastly improved sensitivity, might finally catch these cosmic oddities in the act. Until then, every strange ripple in the data sparks the same thrilling question. Are we hearing the universe play by familiar rules, or is it whispering secrets we're only beginning to decode? Beneath the drama of individual black hole collisions, there's a subtler soundtrack to the cosmos, a faint, ceaseless hum made of countless gravitational waves from mergers too distant or ancient to distinguish. This is the stochastic background, the universe's equivalent of hearing a stadium roar from blocks away, the combined echo of every black hole and neutron star collision since the dawn of time. Unlike LIGO sharp chirps, this signal isn't a single event but a collective murmur, saturating space-time like static between radio stations. To catch this whisper, scientists are turning nature's most precise timekeepers into gravitational wave detectors, pulsars. These spinning neutron stars beam radio waves with metronome-like regularity, some ticking more accurately than atomic clocks. When a gravitational wave passes through, it minutely stretches and squeezes the space between Earth and these cosmic lighthouses, causing their pulses to arrive a fraction early or late. By monitoring networks of pulsars across the galaxy, like an interstellar spiderweb, researchers can spot the telltale correlations in their timing glitches, revealing the background hum's fingerprint. The hunt is already yielding tantalizing hints. In 2023, multiple pulsar timing array collaborations reported a shared signal in their data, a low-frequency buzz consistent with theorists' predictions for the stochastic background. The likely culprits, not the stellar mass collisions LIGO sees, but the far slower dances of supermassive black hole binaries, each weighing billions of suns. These cosmic heavyweights take centuries to complete a single orbit, emitting gravitational waves with wavelengths so long they'd stretch from Earth to the Sun. What's fascinating is how this hum encodes cosmic history. Its amplitude could reveal whether supermassive black holes merge efficiently or stall in endless waltzes. Its frequency spectrum might betray exotic physics, like cosmic strings, hypothetical wrinkles in spacetime left over from the Big Bang, and if the signal is stronger than expected. That could mean black holes merged more often in the early universe, painting a picture of a far more violent cosmic adolescence than we'd imagined. The challenge is untangling this signal from noise. Pulsar timing must account for everything from the solar wind's interference to the Milky Way's gravitational jostling. It's like trying to hear a conversation in a crowded cafe where every chair scrape and clinking cup might be a false lead. But with more pulsars added to the arrays and decades of data rolling in, the hum is coming into focus not as a single note, but as the chorus of the universe itself, sung by black holes we'll never see, in keys we're only learning to hear. When black holes collide, the aftermath isn't always peaceful sometimes. The newborn black hole gets punted across space like a cosmic soccer ball. These black hole kicks can launch these monstrous objects at speeds over 5,000 kilometers per second, fast enough to escape entire galaxies. Gravitational waves aren't just revealing these violent ejections, they're letting us measure the kicks with precision, exposing the chaotic physics behind the universe's most powerful recoils. The secret lies in the merger's asymmetry. When two black holes spiral toward collision, their spins and orbits act like cosmic catapults. If their masses or spins are mismatched, say, one is rapidly rotating while the other barely moves, the outgoing gravitational waves carry momentum away unevenly during the merger. The result, the final black hole recoils in the opposite direction, obeying Newton's third law on a galactic scale. Imagine firing a rifle where the bullet is made of pure spacetime curvature. The kickback flings the black hole across its host galaxy. LIGO detections have caught these kicks in action. One notable event, GW 1929, showed a black hole getting a 3,000 km per second shove, enough to send it flying between stars like a rogue cannonball. But the real shocker came with GW 1915, where the kick might have exceeded escape velocity for even the largest galaxies. If confirmed, that black hole is now drifting through intergalactic space, completely untethered from any star cluster or galaxy. What's wild is how these kicks solve cosmic mysteries. Astronomers have long spotted hypervelocity stars racing through the void, but black holes moving this fast were purely theoretical. Gravitational waves prove they're real and far more common than we thought. Some might even explain oddball quasars flickering in unexpected corners of the universe, their supermassive engines possibly launched there by ancient kicks. The data also hints at surprises. A few mergers show kicks angled strangely, suggesting the black holes got an extra gravitational slingshot from nearby stars or gas. Others imply that the most massive black holes might resist kicking entirely, like sumo wrestlers too heavy to budge. Every new detection adds another piece to the puzzle, revealing how these cosmic behemoths get tossed around like particles in an accelerator. Here's the kicker, pun intended. These velocities aren't just curiosities, they shape galaxies. A black hole ejected from a galaxy's core could leave its stars without a gravitational anchor, disrupting orbits for millennia. Or it might carry a disk of glowing gas with it, seeding new star formation like a cosmic tornado. Some theorists even speculate that primordial black hole kicks could have distributed dark matter unevenly in the early universe. Gravitational waves turn each recoil into a physics lab. By comparing the kick's speed to the merger's spin and mass measurements, scientists test general relativity in extreme regimes where space gets dragged like taffy. Some kicks even suggest hints of exotic physics like extra dimensions, subtly altering how momentum bleeds into gravitational waves. So next time you hear about black holes merging, remember, it's not just a collision. It's a cosmic car crash, complete with debris in this case, a trillion-degree spacetime warp getting hurled into the void. And thanks to gravitational waves, we're not just bystanders. We're the cosmic traffic cops clocking these speedsters as they rewrite the rules of galactic escape. Star-shredding black holes don't just light up the cosmos, they make it ring like a gong. These spectacles, called tidal disruption events, occur when a star wanders too close to a black hole's gravitational grip, stretching it into a glowing stream of plasma before swallowing it whole. For decades, astronomers studied these violent meals through bursts of X-rays and ultraviolet light. But now, gravitational waves offer a front-row seat to the moment spacetime itself gets rattled by the carnage. Picture a star like our Sun approaching a black hole 10 million times more massive. As it crosses the event horizon's doorstep, tidal forces stretch it vertically while compressing it horizontally, a process called spaghettification. This cosmic tug-of-war unleashes flares brighter than entire galaxies, but hidden in the chaos is another signature: low-frequency gravitational waves pulsing as the black hole's gravity rips the star apart. Unlike the sharp chirps of black hole mergers, these waves rise and fall like the groans of a sinking ship, carrying details about the star's composition and the black hole's appetite. The first hints of this connection came in 2021, when researchers matched a flare from a distant galaxy with peculiar gravitational wave noise in LIGO data, not quite a merger, but not random static either. Analysis suggested the waves might have come from a black hole abruptly gaining mass as it engulfed a star, like spacetime recording the exact moment a cosmic predator took a bite. While not yet definitive, such events could become routine with next-gen detectors. What makes these disruptions so valuable is their dual messenger nature. The light reveals the star's death, throws how its material forms swirling accretion disks or gets blasted into jets at near light speed. Meanwhile, gravitational waves encode the black hole's mass and spin with precision no light-based measurement can match. Combined, they paint a 3D portrait of some of the universe's most extreme environments. Some disruptions might even solve a black hole paradox. When stars get shredded, their debris sometimes forms fleeting, quasi-periodic eruptions, flares that pulse rhythmically for months. Theorists suggest these could trace a second, smaller black hole orbiting the primary, stirring the stellar debris like a spoon in soup. Gravitational waves could confirm these hidden duos, exposing black hole binaries we'd never spot otherwise. Every shredded star is a temporary laboratory for extreme physics. The flares test how matter behaves under crushing gravity, while the waves probe how spacetime responds to sudden, asymmetric feasts. Future detections might even catch intermediate mass black holes, elusive middleweights suspected of lurking in dwarf galaxies by the unique frequency of their stellar meals. It's a brutal but beautiful synergy. To understand how black holes grow, we're learning to listen as they dine. At the edge of a black hole's event horizon, physics as we know it reaches its breaking point. Here, gravity warps spacetime so violently that it should, in theory, begin to reveal its quantum underpinnings, flickering like static on the cosmic radio between Einstein's relativity and the bizarre rules of the quantum world. Gravitational waves might be our only shot at eavesdropping on this frontier, carrying faint whispers of a theory that's eluded us for a century: quantum gravity. Picture the chaotic final moments of two black holes colliding. As their event horizons stretch and merge, quantum effects should, according to some theories, cause microscopic fluctuations in the fabric of spacetime itself. These aren't the smooth curves of general relativity, but jittery, pixelated tremors, like the surface of a pond disturbed by invisible raindrops. If these fluctuations exist, they'd imprint onto the gravitational waves emitted during the merger's ring-down phase, subtly altering how the waves fade. It's akin to hearing the difference between a church bell's pure tone and one with a faint digital glitch, a signature that spacetime itself might be quantized at the tiniest scales. The hunt for these fingerprints is already underway. Some researchers are scouring LIGO data for anomalous echoes in black hole mergers repeating ripples that could suggest quantum structure near event horizons. Others are looking for deviations in how gravitational waves polarize, which might betray extra dimensions or exotic particles lurking in gravity's quantum foam. Even the slightest mismatch between observed waveforms and Einstein's predictions could be the crack that leads to a new paradigm. The stakes couldn't be higher. Uniting quantum mechanics and gravity isn't just an academic exercise, it's the key to understanding the universe's earliest moments, where quantum fluctuations in the newborn cosmos ballooned into galaxies. Black holes, those cosmic shredders of information, might also be the Rosetta Stones that finally let us read gravity's quantum code. Every merger we detect is another roll of the dice, another chance that one of these cosmic crashes will carry a signature strange enough to rewrite physics. Until then, we're left listening closely, waiting for spacetime itself to stutter. Think of spacetime like a trampoline stretched tight, a smooth, flat surface when undisturbed. Now imagine dropping two bowling balls onto the fabric, watching them orbit each other rapidly before colliding with a thud. That's essentially what happens when black holes merge, except instead of a trampoline, it's the very fabric of reality that warps under their immense gravity. Gravitational waves are the ripples sent racing outward from that collision, stretching and squeezing spacetime itself as they pass. But here's the twist: these waves don't just move through spacetime. They temporarily reshape it, compressing distances in one direction while expanding them in another, like an invisible cosmic accordion. To grasp how this distortion works, picture a grid of stars plastered across the sky. As a gravitational wave passes Earth, it doesn't actually move those stars. Instead, it alters the space between them. In one moment, the grid stretches horizontally while squishing vertically. Nanoseconds later, the effect reverses, as if the universe is breathing in 4 dimensions. Laser interferometers like LIGO exploit this by measuring how the waves minutely change the length of their detector arms, a shift so small it's like detecting a hair's width change in the distance to Alpha Centauri. The strangest part, these distortions aren't just mathematical abstractions. If you were floating near a merging black hole pair not recommended, you'd literally see your surroundings morph. A circular clock would appear to flatten into an oval, then stretch sideways, its ticks speeding up and slowing down as spacetime itself pulsed. Even light would bend oddly, creating funhouse mirror effects without any mirrors. This isn't just theory. When LIGO detects a wave, it's catching that exact stretching and squeezing in real time, proving spacetime is dynamic, elastic, and alive with vibration. What makes this so groundbreaking is how it flips our intuition about gravity. Newton saw it as a force pulling objects together. Einstein reimagined it as curves in spacetime's geometry. But gravitational waves reveal something wilder. Spacetime isn't just curved, it's flexible, capable of oscillating in precise, measurable patterns. Each wave carries a snapshot of the collision that birthed it, encoding the black hole's masses, spins, and even the angle at which they crashed. It's as if spacetime itself keeps forensic records of cosmic violence, written in a language of strain and compression. The implications ripple across physics. If spacetime can wave, might it also crack? Could it harbor microscopic quantum textures we've yet to detect? Every gravitational wave we catch is a reminder that the stage of the universe isn't static. It's a living, breathing entity, vibrating with the aftershocks of cataclysms we're only beginning to hear. Astronomers expected the universe to serve up black holes of all sizes, but when gravitational wave detectors started listening, they noticed something odd. Between about 50 and 120 solar masses, the cosmos seems to have misplaced its black holes. This isn't just a cosmic accounting error, it's a glaring gap that challenges our understanding of how stars live, die, and collapse into darkness. The mystery stems from stellar physics. Stars between roughly 60 and 130 solar masses face a catastrophic fate called pair instability supernova, explosions so violent they leave nothing behind, not even a black hole. When such a star's core heats up, particle collisions start creating electron-positron pairs instead of sustaining pressure. The star's core collapses abruptly, triggering runaway fusion that obliterates it completely. This process should carve a clean hole in the black hole mass spectrum. But here's the puzzle. Gravitational wave detectors keep catching black holes that seem to bypass this rule. Take the 85 solar mass black hole in GW190521. By all rights, it shouldn't exist. It's smack in the middle of the forbidden zone. One explanation: this might be a second-generation black hole, born from earlier mergers of smaller objects. Imagine 240 solar mass black holes colliding. Their offspring would dodge the pair instability limit entirely, like building a heavyweight boxer by stitching together middleweights. Another clue comes from spin measurements. Some gap objects rotate peculiarly fast, hinting at violent past collisions that rev them up, yet the plot thickens. If mergers are filling the gap, why aren't we seeing more black holes in the lower end of this range? And why do some galaxies host X-ray binaries with black holes near the gap's edge, but never squarely inside? It's as if the universe has invisible no parking signs at certain masses. Some theorists propose exotic solutions. Maybe ultra-rapid rotation stabilizes massive stars against pair instability, or perhaps dense environments like globular clusters offer escape routes from total destruction. Every new gravitational wave detection sharpens the mystery. Some gaps might be observational. LIGO simply isn't sensitive to quieter mergers at certain masses. But if future observatories like the Einstein telescope keep finding outliers, we might need to rewrite the stellar rulebook. For now, this cosmic missing mass problem remains one of gravitational wave astronomy's most tantalizing puzzles. A silent void where the universe's heaviest stars apparently vanish, only to reappear as black holes that defy the rules of their own creation. For centuries, astronomy meant one thing: studying light. Telescopes collected photons across the spectrum, from radio waves to gamma rays, building our cosmic understanding wavelength by wavelength. But gravitational waves shattered that single-sense paradigm, introducing an entirely new way to experience the universe, not through light but through space-time's vibrations. The real revolution, however, erupted when we realized these two messengers could work together. Like witnesses describing the same crime from different angles, gravitational waves and electromagnetic signals combined to reconstruct cosmic events with unprecedented clarity, a technique now called multi-messenger astronomy. The power of this approach exploded into view with GW170817, the neutron star collision that dazzled both LIGO detectors and telescopes worldwide. Here's why it was transformative. Gravitational waves arrived first, pinpointing the event's location and revealing the star's death spiral. 2 seconds later, a Fermi satellite caught a gamma-ray burst, the universe's most energetic flash from the same patch of sky. Within hours, optical telescopes spotted a glowing kilonova, its light curving through ultraviolet and infrared over weeks. Each messenger brought unique clues. The gravitational waves detailed the star's masses and spins. The gamma rays confirmed their collision triggered a relativistic jet. The kilonova's evolving colors exposed heavy elements freshly forged in the cosmic furnace. Together, they didn't just tell a story, they rendered it in 3D IMAX detail. But multi-messenger astronomy doesn't stop there. Some cosmic cataclysms, like supermassive black holes shredding stars, might emit neutrinos, ghostly particles that slip through matter undetected. Others, like pulsar flares, could produce cosmic rays, high-energy protons raining down on Earth's atmosphere. Imagine triangulating an event with gravitational waves timing the black hole's vibrations, telescopes capturing the stellar debris' glow, and neutrino observatories sensing the particle avalanche from deep underground. It's the ultimate cross-examination of the cosmos, where each messenger compensates for the other's blind spots. Light gets absorbed by dust, gravitational waves plow straight through. Waves lack directional precision, gamma rays narrow the search. This synergy is already cracking long-standing puzzles. Take fast radio bursts, mysterious millisecond flashes that might originate from magnetars or colliding neutron stars. If a burst coincides with a gravitational wave chirp, it could confirm theories about their origins. Similarly, pairing gravitational waves with neutrino detectors might expose hidden supernova cores too enshrouded in dust to see optically. Even dark matter searches benefit. Certain exotic particles could trigger subtle gravitational wave echoes when they interact with black holes. The future promises even wilder collaborations. Next-generation detectors like the Einstein telescope will localize mergers so precisely that robotic telescopes can swarm the sky within seconds. Space-based gravitational observatories like LISA might one day trace supermassive black hole mergers while JWST peers at the resulting quasar fireworks. And if we ever detect a supernova's gravitational waves alongside its neutrino pulse, we'll witness a star's death throes in real time, from core collapse to shockwave, like an interstellar medical scan. Multi-messenger astronomy isn't just adding tools to our cosmic toolkit. It's teaching us to perceive the universe in symphonies rather than solo performances, where spacetime's vibrations, light's kaleidoscope, and particles' whispers together compose a fuller, richer portrait of reality. Every coordinated detection doesn't just solve mysteries, it reveals how deeply interconnected the cosmos truly is. Right now, gravitational wave astronomy is undergoing a quiet revolution, not in the cosmos but in the detectors themselves. While LIGO and Virgo have already rewritten textbooks, their next-generation upgrades promise to turn today's whispers into tomorrow's shouts, catching collisions so faint they'd currently vanish into the static. Imagine upgrading from a backyard telescope to the Hubble overnight. That's the leap coming in the next decade. The centerpiece of this transformation is LIGO, a Plus upgrade, set to go online by 2025. By swapping out its laser system for one twice as powerful and installing ultra-reflective new mirrors, the detector will spot mergers up to twice as far away, effectively surveying 8 times more volume of the universe. It's like giving the observatory cosmic hearing aids, allowing it to catch black hole mergers from epochs when galaxies were just beginning to form. But the real game changer lies in the quantum realm. A cutting-edge technique called quantum squeezing will manipulate Heisenberg's uncertainty principle itself, reducing quantum noise that currently drowns out the faintest signals. Picture trying to hear a pin drop in a thunderstorm, then suddenly inventing noise-canceling headphones. That's the precision we're talking about. Meanwhile, Europe's Virgo detector isn't sitting still. Its upcoming Advanced Virgo Plus configuration will tackle a different limitation: low-frequency sensitivity. While LIGO excels at hearing the high-pitched chirps of stellar mass collisions, Virgo's upgrades aim to catch the deeper notes of intermediate mass black holes by suspending its mirrors in an even more delicate dance. They're also addressing an ironic vulnerability: rainfall. The original Virgo's location in Italy's countryside meant seismic noise from passing trucks, and even heavy storms could disrupt measurements. The new design incorporates active vibration isolation, so sophisticated it could filter out footsteps near the detector while still sensing space-time ripples from a billion light-years away. But the most exciting developments might be happening beyond Europe and America. India's upcoming LIGO India, slated for 2030, will complete a global trifecta of detectors. Positioned near Hingoli, its geographic separation from the existing LIGO sites will dramatically improve sky localization, pinpointing mergers so precisely that telescopes can swivel to the right patch of sky within minutes instead of hours. Then there's Japan's Kagra, already online but preparing major upgrades. Buried deep inside Mount Aikno to shield it from Earth's tremors, Kagra has a unique ace: cryogenic mirrors cooled to -250 degrees Celsius. At these temperatures, mirror coatings become so still they barely jiggle from thermal noise, letting the detector sense waves that would otherwise be lost in the atomic chatter of warm materials. The collective impact of these upgrades, a gravitational wave internet where detectors hand off signals like relays. A merger might first register in Louisiana, then milliseconds later in Italy, then India, each timestamp helping triangulate the event with surgical precision. Future networks could detect over 1 collision per hour, transforming these phenomena from rare cosmic jewels into routine data points. And with each upgrade, we're not just adding volume, we're tuning into new cosmic channels. Some upgrades specifically target continuous waves from spinning neutron stars, while others optimize for the low growls of supermassive black holes on century-long collision courses. What's thrilling is how these technical leaps will intersect with new science. Imagine catching a neutron star merger so close we could watch its aftermath for years as the remnant collapses into a black hole. Or spotting a black hole swallowing a neutron star with enough detail to finally crack the mystery of what happens at the edge of an event horizon. There's even talk of detecting gravitational lensing in real time, watching a single black hole merger's waves arrive multiple times as they're bent around intervening galaxies. This isn't just incremental progress, it's the dawn of gravitational wave astronomy's golden age. Every upgrade, every new detector is like adding another instrument to the cosmic orchestra, letting us hear harmonies we never knew existed. And as these machines approach their theoretical limits, they're doing more than just listening to the universe, they're teaching us how to understand its deepest rhythms. While LIGO revolutionized our ability to hear the high-pitched chirps of stellar collisions, some of the universe's most monumental events rumble at frequencies too low for ground-based detectors to catch, like trying to hear a whale song with a microphone designed for hummingbirds. That's where LISA comes in. The Laser Interferometer Space Antenna isn't just another observatory upgrade, it's an entirely new way to listen to the cosmos, floating freely in space with laser arms stretching 2.5 million kilometers long. Unlike Earth-bound detectors plagued by seismic noise and arm-length limitations, this triangular fleet of spacecraft will tune into gravitational waves with wavelengths so vast they could swallow our entire solar system. The targets, supermassive black hole binaries, cosmic duos weighing millions or billions of suns, locked in gravitational waltzes that can last centuries before their final collision. These aren't the quick mergers LIGO spots, they're slow, stately dances where a single orbit might take months. The gravitational waves they emit are equally languid, oscillating at frequencies around 1 MHz, 1,000 times lower than LIGO range. But what they lack in pitch, they make up for in sheer power. A pair of supermassive black holes merging could pump out gravitational waves with 1 trillion times the energy of all the stars in the Milky Way combined, warping spacetime on galactic scales. LISA design is as elegant as it is ambitious. 3 identical spacecraft will trail Earth in a heliocentric orbit, forming a perfect equilateral triangle connected by laser beams. As gravitational waves pass through, they'll minutely alter the distances between spacecraft, shifting them by mere picometers, or less than the width of an atom. To isolate these infinitesimal changes, each craft will house free-floating test masses shielded from solar wind and cosmic rays, essentially creating the quietest listening environment in history. It's like trying to detect a grain of sand dropped on a piano string from across a football field. While the piano is in a hurricane, the science LISA will unlock reads like a cosmology wishlist. By tracking how supermassive black hole binaries spiral together over years, we'll finally solve the final parsec problem, the mystery of whether these giants overcome their orbital stall near merger or need help from gas disks or star clusters. Their waveforms will map spacetime's warping near-event horizons with unprecedented detail, testing if black holes really have no hair as general relativity claims. Some waveforms might even carry hints of extra dimensions, their subtle distortions betraying hidden folds in reality. But the real showstoppers could be the surprises. LISA might catch the moment a supermassive black hole shreds a white dwarf star, a process emitting both detectable gravitational waves and visible fireworks. It could spot intermediate mass black holes, those elusive cosmic middleweights as they merge in dwarf galaxies. Some theorists even speculate it might detect exotic phenomena like cosmic strings, hypothetical spacetime defects left over from the Big Bang that would vibrate with unique gravitational signatures. What makes LISA truly revolutionary is its timescale. While LIGO captures mergers in seconds, LISA will observe some systems for decades, watching their orbits decay in real time like a cosmic stopwatch ticking toward collision. This long baseline transforms gravitational waves from snapshots into movies, letting us witness the slow-motion build-up to the universe's most violent events. By the 2040s, when LISA launches, we won't just be hearing the cosmos, we'll be tuning into its deepest, most resonant frequencies, uncovering rhythms that have pulsed through space-time since the first galaxies formed. Deep in the Milky Way, a network of dead stars keeps perfect-time cosmic lighthouses blinking with such metronomic precision they rival atomic clocks. These pulsars, rapidly spinning neutron stars that beam radio waves across the galaxy, have become humanity's most unlikely gravitational wave detectors. Unlike LIGO laser beams or LISA orbiting spacecraft, pulsar timing arrays transform entire galaxies into instruments, using the natural rhythm of these celestial timekeepers to sense spacetime's faintest tremors. Here's how it works. As a gravitational wave passes between Earth and a pulsar, it minutely stretches and squeezes the fabric of space along its path. This distortion alters the distance the pulsar's radio signals must travel, causing its pulses to arrive at Earth ever so slightly early or late, shifts measured in billionths of a second. Alone, one pulsar's timing glitch might be dismissed as random noise, but monitor dozens across the galaxy and a pattern emerges, correlated delays that ripple across the array like footsteps on a spiderweb, betraying a gravitational wave's passage. The quarry in this hunt, the stochastic background, a collective hum from all the universe's supermassive black hole binaries, each orbiting too slowly for LIGO to hear. Imagine countless pairs of these cosmic titans, separated by light years but locked in gravitational dances that take years to complete a single orbit. Their waves overlap into a cacophony, like hearing every violin in an orchestra play slightly out of sync. Pulsar timing arrays isolate this murmur not by detecting individual mergers, but by catching the statistical fingerprint of their combined rumble across light years. Recent breakthroughs have turned this from theory into tantalizing reality. In June 2023, multiple international collaborations including Nanograv in North America, the European Pulsar Timing Array, and others announced they'd found a common signal in their pulsar networks. The data revealed a background hum consistent with predictions for supermassive black hole mergers, with waves so low frequency their wavelengths could stretch from Earth to the Sun and back. It's as if we've tuned into the universe's deepest bass note, a vibration that takes years to complete a single cycle. What makes this technique so powerful is its timescale. While LIGO captures brief chirps lasting seconds, pulsar timing arrays operate on decadal timelines, patiently assembling a cosmic jigsaw puzzle one monthly observation at a time. The most stable pulsars, like the famous millisecond pulsar PSR J1937+21, have spins so regular that deviations exceeding a few hundred nanoseconds stand out as potential gravitational wave signatures. To achieve this precision, astronomers account for everything from the solar wind's interference to the Milky Way's gravitational field, effectively turning our galaxy into a calibrated laboratory. Beyond black holes, these arrays could uncover even stranger phenomena. Primordial gravitational waves from the Big Bang might leave subtler imprints at these frequencies, carrying whispers from cosmic inflation. Cosmic strings, hypothetical spacetime defects theorized to form in the early universe, could create distinctive bursts in the data if they snap like overstretched rubber bands. Some speculate we might even detect the collective hum of all the universe's binary black holes, since time began a background so ancient it predates the first stars. The future of this field lies in expansion and refinement. New telescopes like the Square Kilometre Array will discover hundreds more pulsars, tightening the cosmic web. Longer observation periods will tease apart whether the background is truly isotropic or carries directional clues to nearby supermassive binaries. And as gravitational wave astronomy matures, pulsar timing may bridge the gap between Lisa millihertz realm and LIGO audio band detections, giving us a continuous spectrum of the universe's vibrations. For now, every irregular tick in a pulsar's rhythm is a potential message not from the star itself, but from the warped spacetime between us. These spinning relics have become more than celestial curiosities. They're the galaxy's own gravitational wave observatory, patiently recording the universe's deepest rhythms one radio pulse at a time. Gravitational waves don't just ripple through spacetime, they twist it, leaving behind hidden fingerprints in their polarization that could crack open the universe's best-kept secrets. Much like light waves oscillate in specific orientations, gravitational waves also have distinct polarization patterns, governed by how they stretch and squeeze space as they travel. But here's where it gets revolutionary. The way these waves polarize isn't just a quirk of Einstein's relativity, it's a litmus test for whether his theory holds up, or if there's something stranger lurking in the cosmos. Einstein's equations predict gravitational waves should have two primary polarizations, whimsically named plus and cross, for how they deform a ring of test particles, first squeezing it vertically while stretching horizontally plus, then diagonally cross. But alternative theories of gravity, like scalar tensor or massive gravity models, introduce extra polarizations. Some theories propose a breathing mode where space expands and contracts uniformly like a balloon inflating and deflating. Others suggest longitudinal waves that push and pull particles along the direction of travel, like an accordion's bellows. If these exotic polarizations exist, they'd betray physics beyond Einstein's framework, hinting at hidden dimensions, new particles, or even modifications to gravity itself. The hunt for these anomalies is already underway. When LIGO detects a gravitational wave, its twin detectors positioned at right angles in Louisiana and Washington act like cosmic ear trumpets, sensitive to specific polarization orientations. By comparing the signals at both sites, scientists can reconstruct the wave's polarization pattern. So far, every detection aligns neatly with general relativity's predictions. But the real excitement lies in the outliers, events that don't quite fit. In 2017, a peculiar signal from a black hole merger showed faint hints of an extra polarization mode, sparking a firestorm of debate. Was it noise, a calibration glitch, or the first whisper of new physics? Future observatories like LISA and the Einstein telescope will turn this hunt into a precision sport. With detectors spaced across continents, or in LISA's case, across millions of kilometers, they'll create a sprawling network capable of mapping polarization in 3D. Imagine distinguishing a gravitational wave's twist as precisely as a prism splits light. Such resolution could reveal whether gravity behaves differently in extreme environments, like near supermassive black holes or in the early universe's high-energy chaos. Some theories even suggest that polarized waves might carry imprints of quantum gravity, their subtle distortions encoding how spacetime behaves at Planck-scale energies. The stakes are cosmic. If we find evidence of extra polarizations, it wouldn't just tweak relativity, it could rewrite our understanding of gravity's fundamental nature. Are there undiscovered forces acting alongside it? Does gravity leak into higher dimensions? The answers might ripple toward us in the next gravitational wave we catch, hidden in the silent swirl of spacetime itself. Every black hole collision sends ripples through spacetime, but the real magic happens in the aftermath when the newborn black hole settles into its final form, vibrating like a struck bell. These oscillations, known as quasi-normal modes, produce distinct gravitational wave tones that reveal the black hole's hidden structure with astonishing precision. It's as if the cosmos has handed us a tuning fork for the universe's darkest objects, letting us decode their secrets through spacetime's own symphony. Take the very first black hole merger LIGO detected, GW150914. After the collision's initial chirp, the signal didn't just cut off, it faded in a characteristic ring down, like the dying hum of a gong. Hidden in that decay were multiple overlapping frequencies, each corresponding to a specific vibrational mode of the new black hole's event horizon. The dominant tone, a pitch roughly 250 times higher than middle C, revealed the black hole's final mass. But the overtones, fainter and more complex, exposed something deeper, the exact shape of spacetime's warping near the event horizon. This technique, called black hole spectroscopy, works much like how chemists identify elements by the light they emit. Just as hydrogen and helium have unique spectral fingerprints, every black hole's ring down produces gravitational wave frequencies determined solely by its mass and spin. The ratios between these tones become a cosmic barcode, one that general relativity predicts with mathematical exactness. When LIGO measurements matched Einstein's equations to within 99.9% accuracy, it wasn't just a victory for theory. It proved we can hear a black hole's structure as clearly as a musician distinguishes notes on a scale. What makes this so groundbreaking is how these tones probe extremes unreachable by any other means. The fastest oscillations, lasting mere milliseconds, trace how spacetime rebounds from the violent merger, while slower modes reflect the black hole's gradual relaxation into perfect smoothness. Some frequencies even hint at phenomena near the event horizon's edge, where gravity's pull stretches matter into quantum spaghetti. If deviations from Einstein's predictions ever appear in these tones, they might unveil quantum gravity effects or exotic matter lurking just beyond the point of no return. The real surprise has been how musical black holes turn out to be. While isolated black holes are famously silent, no hair, no light, no sound, mergers make them sing and the songs follow precise harmonic rules. The fundamental tone and its overtones relate to each other like notes in a chord, their spacing encoding the black hole's properties. Some researchers have even translated these frequencies into audible sounds, revealing an eerie resemblance to Tibetan singing bowls, a cosmic resonance that seems almost designed for discovery. Future detectors like the Einstein telescope will turn spectroscopy into a precision art, potentially distinguishing tones from black holes with exotic interiors or those wrapped in dark matter halos. It's like upgrading from a toy xylophone to a grand piano. Suddenly, we'll hear nuances in the cosmic melody that were always there, just too faint for our instruments to catch. Every new ring down we analyze doesn't just add to our catalog of black holes. It fine-tunes our understanding of how spacetime itself vibrates under the most extreme conditions imaginable. Among the most exotic relics predicted by cosmology are cosmic strings, hypothetical flaws in spacetime thinner than a proton but stretching across the entire universe, left over from the fiery chaos of the Big Bang. Picture the universe as a vast sheet of ice freezing rapidly. Cracks might form as it solidifies unevenly. Cosmic strings would be those cracks, one-dimensional defects where spacetime itself is pinched into unimaginable density, carrying more mass per inch than Mount Everest. If they exist, these bizarre threads would warp spacetime so severely that their gravitational wave signatures would be unlike anything else in the cosmos. Detecting a cosmic string would be like finding a frozen lightning bolt from the birth of reality. Unlike black hole mergers that produce transient chirps, strings would generate continuous gravitational waves as they oscillate or snap, sending out bursts of spacetime ripples at frequencies ground-based detectors like LIGO could potentially catch. The most telltale sign, a gravitational wave signal that doesn't fade but persists with near-perfect regularity, like an endlessly vibrating violin string. Some theories even suggest these strings might form loops, collapsing in violent bursts that release gravitational waves across multiple frequencies simultaneously, a cosmic chord instead of a single note. The mathematics behind these predictions is mind-bending. A string just 1 kilometer long might weigh as much as an entire planet, yet be so narrow that it could pass through Earth unnoticed except for the gravitational shock waves it would emit. If two strings crossed or a loop fragmented, the event could unleash energy rivaling a supernova, all in the form of gravitational radiation. Simulations show these bursts would have a distinctive fingerprint, a sharp, asymmetric spike in the waveform, completely different from the smooth inspirals of colliding black holes. While no confirmed detection exists yet, gravitational wave astronomy offers our best shot at finding these ghosts. Pulsar timing arrays might have already picked up their collective hum in the stochastic background, while future space-based observatories like LISA could spot the low-frequency oscillations of string loops larger than our solar system. Even more thrilling are the theoretical possibilities if strings are discovered. Their properties could reveal details about the universe's first trillionth of a second, including which grand unified theory of physics correctly describes that epoch. Some models even link cosmic strings to dark matter or other hidden sectors of particle physics. The search isn't just about confirming a wild prediction, it's a direct probe into the quantum structure of spacetime itself. Finding a cosmic string would mean the universe preserves fossils from its earliest moments in ways we never imagined, etched not in stone or light, but in the very fabric of gravity. Until then, every unexplained ripple in the data keeps the hope alive that somewhere out there, spacetime is humming with the echoes of defects older than time. Behind every gravitational wave detection lies a computational symphony, a supercomputer running simulations so precise they can predict spacetime's ripples down to the quantum noise floor. These aren't just fancy animations, they're mathematical battlefields where Einstein's equations get stress-tested against reality, with entire clusters of processors grinding for weeks just to model milliseconds of a black hole merger. The goal, to build a library of theoretical waveforms so exhaustive that when LIGO catches a real signal, scientists can match it like a fingerprint, revealing the collision's hidden physics. Take the software Einstein toolkit running on machines like the NSF's Frontier supercomputer. To simulate two neutron stars colliding, it must solve over 10 million interlinked equations per time step, tracking fluid dynamics, magnetic fields, and spacetime curvature simultaneously. Each simulation consumes thousands of CPU hours, generating petabytes of data just to predict how the star's crust shatters, how their cores melt into quark-gluon plasma, and how their combined mass rings spacetime like a bell. The complexity is staggering. A single miscalculation in the neutron star's equation of state, how matter behaves under crushing pressure, could skew the predicted waveform entirely. But why go through this computational marathon? Because nature doesn't hand us answers, it gives us riddles wrapped in noise. When LIGO detects a gravitational wave, the raw signal looks like static punctuated by a faint wobble. Supercomputers provide the templates to decode it. By comparing the observed wave against millions of precomputed scenarios, varying masses, spins, collision angles, researchers can reverse engineer the event's parameters with surgical precision. It's like identifying a song by its musical notes, except the notes are distortions in the fabric of reality. The stakes ramp up with unexpected detections. When GW 1921 revealed an 85 solar mass black hole, a size theory claimed shouldn't exist, supercomputers raced to test alternatives. Was it a second-generation merger, a primordial black hole? Simulations exploring these possibilities now fill entire data archives, each requiring novel coding tricks. Some models even incorporate speculative physics, like exotic dark matter cores or extra dimensions, just to see if their waveforms match the anomalies in LIGO data. What's truly revolutionary is how these simulations push hardware limits. Modeling a black hole merger with full general relativity requires adaptive mesh refinement, a technique that zoins computational resources onto the most warped regions of spacetime, like a cosmic magnifying glass. Meanwhile, machine learning accelerates the hunt, with neural networks trained on synthetic data to spot real signals buried in noise, the latest breakthrough. Reduced order modeling, which compresses years' worth of simulations into rapid approximations, letting astronomers test theories in hours instead of months. This symbiosis between silicon and spacetime is rewriting astrophysics. Supercomputers don't just interpret gravitational waves, they predict phenomena we haven't even observed yet, like resonant mergers where black holes briefly orbit in perfect harmony before colliding. They've become time machines too. By simulating the universe's first black holes, they offer glimpses into epochs no telescope can see, the next frontier. Real-time multi-messenger astronomy. Imagine a supercomputer spotting a neutron star merger in LIGO data, simulating its expected kilonova brightness and spectrum within minutes, then directing telescopes to the exact patch of sky, all before the optical flash fades. We're not just decoding the cosmos anymore, we're learning to dance with it step by simulated step. Imagine being able to crack open your laptop and join the hunt for black holes. No advanced degree or billion-dollar lab required. That's the reality projects like Gravity Spy have created, turning gravitational wave astronomy into one of the most democratic sciences in history. This isn't just crowdsourcing, it's a full-blown revolution where anyone with an internet connection can help sift through LIGO data, separating cosmic gold from detector glitches with the precision of a seasoned astronomer. Here's how it works. Every time LIGO detects a potential gravitational wave, it's not just a clean chirp, it's buried under a storm of noise. Earthquakes, passing trucks, even lightning strikes create false alarms that mimic real signals. Sorting through these requires something algorithms still struggle with: a human intuition. That's where volunteers come in. Gravity Spy presents users with real LIGO data snippets, training them to recognize telltale patterns through an interface as intuitive as a mobile game. Is that wiggle a colliding neutron star or just a gust of wind rattling the detector's mirrors? Your eyes might spot what a computer misses. The results speak for themselves. Since launching in 2016, over 30,000 volunteers have classified millions of glitches, uncovering subtle signals that automated systems initially dismissed. One standout case involved a faint chirp buried under what looked like random static, dismissed by algorithms as noise until a citizen scientist flagged it. Upon reanalysis, it turned out to be a bona fide black hole merger. These contributions don't just clean up data, they train machine learning models to improve future searches, creating a feedback loop where human and artificial intelligence grow sharper together. What makes this collaboration so powerful is its scale. LIGO generates roughly 1 petabyte of data annually, equivalent to streaming 8 years of high-definition video non-stop. Even with supercomputers, parsing this deluge is Herculean, but distributed across thousands of volunteers, patterns emerge faster. Some participants specialize in whistles, frequency gliding glitches, others in blips, short bursts of noise, developing an almost artistic eye for the data's quirks. The project's forums buzz with discussions rivaling academic conferences, where retirees, high school students, and amateur astronomers debate spectrograms with the rigor of PhDs. Gravity Spy isn't alone in this movement. Platforms like Zooniverse host similar initiatives, while Einstein at Home harnesses idle computing power from volunteers' devices to search for continuous gravitational waves from spinning neutron stars. Together, they're redefining who gets to participate in cutting-edge science. A teacher in Nairobi, a taxi driver in Buenos Aires, a teenager in Oslo all have contributed to papers published in top journals, their names listed alongside professional researchers. The implications stretch beyond astronomy. This model proves that complex science isn't just for elites in ivory towers. It's a collective endeavor where curiosity is the only credential. As detectors grow more sensitive and data volumes explode, citizen science will become indispensable, not optional. Future breakthroughs might not come from a lone genius in a lab, but from a global network of ordinary people, their collective curiosity weaving a safety net to catch whispers from the cosmos that would otherwise slip through the cracks. Detecting gravitational waves isn't just about listening for cosmic whispers, it's about silencing an entire orchestra of earthly racket that constantly threatens to drown them out. LIGO detectors are so sensitive they don't just catch space-time ripples, they pick up earthquakes on the other side of the planet, gusts of wind tapping the walls, even the rumble of a delivery truck passing miles away. These aren't just minor nuisances, they're full-blown signal imposters, mimicking black hole mergers with eerie precision. One infamous false alarm in 2020 was traced back to a lightning strike in Africa, whose electromagnetic pulse traveled through the ground and jiggled LIGO mirrors. Another came from a glitch dubbed the Scratch, caused by a faulty wire vibrating at exactly 180 Hz, a frequency perilously close to real gravitational wave signals. But the quirkiest culprits might be the ones lurking inside the detectors themselves. Thermal noise, the random jiggling of atoms in LIGO mirror coatings, creates a constant hiss equivalent to measuring movements smaller than 1/10,000th the width of a proton. Then there's the parametric instability problem. Laser light bouncing between mirrors can accidentally excite sound waves in the glass itself, making the mirrors hum like tuning forks. Even the quantum uncertainty of the laser photons introduces unavoidable noise, as if the universe itself is blurring the detector's vision at the smallest scales. The solutions are as ingenious as the problems are bizarre. To combat seismic noise, LIGO mirrors hang from a series of pendulums and filters so delicate they can isolate vibrations equivalent to dropping a single grain of sand onto the detector from waist height. The team even monitors global earthquake databases in real time, automatically pausing observations when major tremors occur. For those pesky quantum fluctuations, they've deployed squeezed light, a laser trick that manipulates the Heisenberg uncertainty principle itself, trading precision in one quantum property for better accuracy in another. It's like turning down the universe's static at its source. Then there's the detective work. Each glitch gets a nickname, blip, whistle, koi fish, based on its shape in the data. Teams hunt down origins with forensic zeal. One fast scattering noise turned out to be frost sublimating off cooling pipes, while a recurring helix pattern traced back to a malfunctioning temperature sensor. The Virgo detector in Italy faced its own unique nemesis, thunderstorms. Rainfall vibrations forced engineers to design seismic isolation so advanced it could distinguish between a raindrop's patter and a neutron star's death spiral. What's wild is how these earthly struggles sharpen cosmic discoveries. Every noise filtered means fainter gravitational waves become audible, like turning down the car radio to hear a whisper. Future upgrades will tackle even subtler intruders, from the pressure of sunlight photons hitting the mirrors to the minuscule expansion of metal components as the sun rises and heats the labs. In this endless game of cosmic whack-a-mole, silencing the mundane is the price of hearing the extraordinary. The most thrilling aspect of gravitational wave astronomy isn't what we've found, it's what we haven't yet detected. With every upgrade to our cosmic listening devices, we're peeling back layers of the universe to reveal phenomena so bizarre, they'd make even Einstein do a double take. One tantalizing possibility: entirely new classes of celestial objects lurking in the cosmic shadows, invisible to telescopes but broadcasting their existence through spacetime's vibrations. Take hypothetical quark stars, ultra-dense remnants even stranger than neutron stars. If certain theories hold, these could form when neutron stars get squeezed beyond their breaking point, collapsing into a soup of free quarks. Unlike neutron stars, which emit predictable gravitational waves when they collide, quark stars might produce exotic, dual-tone signals, simultaneous high and low frequencies from their ultra-rigid surfaces fracturing under pressure. There's even speculation about electroweak stars, where conditions are so extreme that electromagnetism and the weak nuclear force merge into a single primordial force, briefly resurrecting physics from the universe's first picosecond. A gravitational wave from such an object could carry fingerprints of these long-lost laws etched into its waveform. Then there's the wild card of modified gravity. Einstein's theory has passed every test so far, but what if black hole mergers in extreme environments, like near the supermassive black hole at our galaxy's core, produce waves that deviate from relativity's predictions? Certain alternative theories suggest gravity could behave differently at cosmic distances or in regions of curved spacetime, imprinting telltale extra wiggles in gravitational wave signals. Imagine detecting a merger where the wave's polarization doesn't match general relativity's template, a smoking gun for new physics hiding in plain sight. Some models even predict bouncing black holes in theories where singularities get replaced by quantum rebounds, producing gravitational wave echoes with a distinctive stamp. The real curveball: signals that defy any conventional explanation. In 2020, the LIGO Virgo team reported a detection dubbed GW1900-2014, a ripple that matched no known astrophysical source. Was it a chance alignment of noise? A rare hierarchical merger where a black hole formed from two earlier collisions got swallowed by a third? Or something entirely unforeseen, like a primordial black hole from the Big Bang meeting a modern stellar mass counterpart? The universe keeps reminding us the most exciting discoveries aren't the ones we're hunting, they're the ones we didn't even know to look for. And while the idea seems straight out of science fiction, even the possibility of artificial gravitational waves, though vanishingly unlikely, can't be entirely dismissed. If a hyper-advanced civilization could harness black hole collisions as energy sources or propulsion methods, the waveforms might carry unnatural symmetries or timing patterns. SETI researchers have half-jokingly proposed algorithms to scan gravitational wave data for technosignatures, unusual harmonics or repeating structures that defy natural explanations. It's a long shot, but in a cosmos full of surprises, why rule anything out? The next era of gravitational wave astronomy will likely rewrite the rules as dramatically as the first detections did. Future observatories could uncover ghost mergers where dark matter interacts via gravity alone, leaving no electromagnetic trace. Space-based detectors might catch the universe's background hum, from cosmic strings, space-time defects left over from the Big Bang vibrating like guitar strings stretched across the cosmos. Or we might stumble upon something far stranger, a phenomenon so unexpected it forces us to reinvent our understanding of reality. One thing's certain, the universe has been keeping secrets in spacetime's vibrations for billions of years, and we're just beginning to eavesdrop. From the first historic chirp of colliding black holes to the faint hum of the cosmic gravitational wave background, these 30 discoveries have shattered our understanding of the universe in ways we're only beginning to grasp. Gravitational waves didn't just add another tool to astronomy's toolbox, they tore open an entirely new sensory dimension, letting us hear the cosmos's darkest secrets. We've witnessed black holes merging at half the speed of light, decoded neutron star collisions that forged gold by the asteroid load, and even glimpsed hints of spacetime's quantum fabric trembling at the edge of detection. Every ripple in spacetime has rewritten the rules, proving that the universe is far stranger, more violent, and more dynamic than we ever imagined. Think about how much has changed in less than a decade. Before LIGO, black hole mergers were theoretical sketches in dusty notebooks. Now we've logged dozens, spotting everything from petite stellar remnants to monstrous intermediate mass outliers that defy stellar physics. We've caught neutron stars ripping each other apart in kilonova explosions so bright they outshine galaxies, confirming in one spectacular moment where half the periodic table's heaviest elements are born. Gravitational waves have even turned pulsars, those spinning stellar corpses, into galactic-scale microphones, tuning into the low growl of supermassive black holes circling each other across billions of years. But the revolution goes deeper than cataloging cosmic crashes. These waves have become precision tools, testing Einstein's relativity in extreme regimes where space and time twist into knots. They've exposed gaps in our knowledge, like the mysterious black hole mass desert, where stars seemingly vanish instead of collapsing, and teased possibilities of entirely new physics, from quantum spacetime foam to extra dimensions. Who could have predicted that listening to spacetime's vibrations would help measure the universe's expansion rate, or that we'd one day debate whether faint echoes in merger data betray quantum effects at event horizons? Yet for all we've learned, the most exciting chapters are unwritten. Right now, upgrades to LIGO, Virgo, and Cagra are pushing sensitivities to new extremes, while upcoming observatories like LISA and the Einstein telescope promise to open entirely unexplored frequency bands. Will we finally detect primordial waves from the Big Bang, or catch a supermassive black hole merger in the act? Could some future signal reveal exotic objects we haven't even dreamed of, quark stars, cosmic strings, or evidence of a holographic universe? The questions outnumber the answers, and that's what makes this golden age of discovery so thrilling. So stay curious. The next gravitational wave detection could arrive tomorrow, a blip in the data that appends textbooks and sends astronomers scrambling for their telescopes. Whether you're a casual stargazer or an aspiring physicist, remember, you're witnessing science history unfold in real time. The universe has been broadcasting its secrets for billions of years. At long last, we've learned how to